Thank you all so much for joining us today. I'll take a minute and introduce myself. My name is Abby Freeman. I'm a research scientist at JPL. I'm one of the co-leads of the workshop. Joining me today are also co-leads Bethany.
Hey folks, I'm Bethany Ehlman, Professor of Planetary Science at Caltech, and just thrilled for all our workshop participants joining, as well as the many dozens of people on the list who are interested in revolutionizing access to the Martian surface. So thank you.
And then also with us today, and one of our short course speakers is Chris Colbert.
Good afternoon, everybody. Thanks for joining. I'll echo Bethany and Abby. I think you'll find this is a really interesting discussion. We're looking forward to some really meaningful and hopefully very energetic discussions about some really interesting topics. So thank you all for joining us.
Yes, and thank you all. Welcome to our revolution. The purpose of the short course today is to get everybody on the same page about the terms about why scientists think we're going to need many Mars surface-based measurements in the future, the state of the current technology, and then also key challenges and opportunities to address these in the future. So as I mentioned, we're all delighted to have you today. And I think we should go ahead and just jump right in with our first speaker. So our first speaker today will be Dr. Don Banfield, who's a professor at Cornell University. He has an expertise in the dynamics and the structures of planetary atmospheres. He's participated in planetary missions across the solar system from Voyager 2 all the way to InSight and the Mars 2020 rover, and is currently developing the next generation of in situ instruments to study terrestrial planet surface interactions. He serves as the Goals Committee Chair of the Mars Exploration Program Analysis Group, or MEPAD. So in this capacity has a really excellent knowledge about what the Mars science community has identified as the highest priority Mars science goals for the next decade. So please join us in welcoming Dr. Banfield, who will be talking to us today about driving science questions for Mars.
Thanks for the nice introduction, Abby. Just one subtle clarification. I'm not actually a professor there. I'm a principal research scientist at Cornell. So I don't teach. Let me share my screen here. Our fearless leaders asked me to talk about the driving science questions for Mars, and these were the charges. What are the current high priority Mars science goals? What can only be answered through in situ science? And what measurements are needed to address these goals? As Abby said, I'm actually the MEPAD Goals Committee Chair. Now let me tell you about MEPAD. That's the Mars Exploration Program Analysis Group. Probably a lot of you are familiar with it, but it is this community organization that its charge is to consider and advocate for the science that can be done at Mars. And one of the aspects of its works is to produce this goals document, which is this living document that we update every 2 to 3 years, reflecting what has happened in the recent past. And specifically, it tries to prioritize the flight measurements that we would do at Mars to address the high priority science investigations. And we just released a version last year. That's the title of it. And I'm the lead author on it, but actually there's a whole slew of people that put most of the work into it. I was the wrangler, and these people did the real work, including, I think Paul is part of our group today. I don't know, maybe somebody else is here that was on this. These are the esteemed colleagues that actually did the writing, and you're probably familiar with many of them and respect them greatly, hopefully. But they did not do everything. This was a community effort. So we actually had a lot of community input with a couple of meetings at the MEPAD meetings for themselves, but also we kicked off this new revision of the document at the 9th Mars Conference at Caltech in July 2019. We got a bunch of community feedback, both written over the internet and also a single live interactive event. And then we finally put out the actual draft. It was supposed to be at LPSC, but that didn't happen. So we put it out March 31st in time to be a reference for the Decadal Survey white papers. Yeah, so how is the actual document is organized around 4 different main themes: life, climate, geology, human exploration. And very briefly, the questions as we express them are: life is determine if Mars ever supported or still supports life. Climate is understand the processes and history of climate on Mars. The geology question is understand the origin and evolution of Mars as a geological system. There's a lot in that one. And then the one that's a little bit different, that's a little more engineering, is human exploration, where we examine what it takes to prepare for human exploration in the near term. We've organized these 4 different questions, these 4 different goals of Mars exploration in terms of the top level goal, and then each one of those has a set of objectives below it. Each objective has sub-objectives, and then even below that there are investigations. So it just it's hierarchical to a great degree, and so it's broken down into small elements that can be addressed, and each of those investigations should have a pretty clear set of measurements that can be made. Many of them, you'll find out, are needed to be done at the surface of Mars, so relevant to this question that we're talking about today. Yeah, so this is just the goals and first level objectives, and I thought I would go through this a little bit in detail, just so that we can see the structure a little bit better. Let me just walk through it. At the top, I don't know if you guys can see my cursor. If the first one is life, if Mars ever supported or still supports life, and the group broke it down into an interesting way. The first sub-objective is to search for life or evidence of past life in environments that have a high potential for habitability and preservation of the biosignatures. And then the second objective is to assess the extent of abiotic organic chemical evolution. So you need to understand, I guess, how organics would be potentially developed at Mars, not through biotic processes, so that you could understand better the context of when you find something you think might be life. Turning to the climate question, we wanted to understand the process and the history of climate on Mars. And I guess I'm not going to read through these directly, but they break down into questions about the state and processes of present-day climate at Mars, and then going a little bit further back in time, the history and processes of climate at Mars in the recent past under different orbital conditions. And that is thinking on timescales of 10,000 to maybe a million years or millions of years. And then finally, the last objective for the climate question is, what is the ancient climate at Mars? And here we're talking about things that happened 1 billion or more years ago. So when Mars presumably was quite different climatically. Okay, turning to the geology goal, understanding the origin and evolution of Mars as a geological system. This is a really big one. And much of what we've done at the surface of Mars has been addressing this already. It breaks down in, they broke it down into 3 things. The first one, which is really the huge one, is document the geologic record that's preserved in the crust and understand and investigate the processes that created and modified that record. So this is most of what we've explored with rovers on Mars to date, and there's still a lot of room for action in this. The next one is talking about the origin and structure of the interior of Mars. So how is it put together? How does it behave? How did it get formed? InSight, for example, has been working on this pretty diligently for the past 2 years. Hopefully we'll keep going for a while longer. And then the third objective of the geology question is to determine the origin and history of the moons of Mars. And we're not going to actually talk about that very much in this talk, or presumably at this workshop, because we're interested in the Martian surface, the planet itself. Okay, turning to human exploration. This breaks down in a pretty logical way, a little bit different than the others, but the first question that is addressed is, how do you actually put people at the surface of Mars with acceptable cost, risk, and performance? And then how do you make sure that they can explore it with extravehicular activity safely and within reasonable cost bounds? And then finally, well, not finally, and then additionally, how can they use in situ resources? And then there's the other 2 questions are biological contamination. That's asking both contamination of Mars and back contamination of the Earth if we send people there. And then finally, there's another bullet that's talking about exploring Phobos and Deimos. And again, we're not going to talk about that very much. This next slide is clearly an eye chart. I'm just showing it to you to suggest that each of those objectives that we just talked about also break down into sub-objectives. And then each of those sub-objectives break down into investigations, which are the specific measurements or set of measurements that we would take. I'm going to go through these, but I hope I can get through them in the time frame. Let me just make sure my timing is going okay. So I'm going to show you a bunch of slides like this, which is each goal, and then the objective and the sub-objectives, and then a synopsis of each of the investigations. And for each of these investigations, I've kind of boiled it down to just a few words. And after that, I put some indication of the priority of that particular investigation. Some of these may be not quite right as new technologies become available. So don't take them super literally. And we kind of like to think that all of the investigations that are in the MEPAD Goals document are important. So even the few that we say are maybe lower priority, maybe those could bubble higher in the ranking if a new technology comes on board that makes them more feasible, or if new investigations or new questions come up. So don't take them too literally, but they are a rough guide of what we think might be the most important questions to be asking. Okay, so for the life question, this is the objective that is relevant to extant life. And the sub-objectives break down to, are there signatures of life present there in regions that would have liquid water? And what is the habitability that would be near the surface or in the deep subsurface? And what is the preservation of biosignatures that were there? So each of these are important questions if you want to understand the evidence of life in the past there. This first one breaks down into what would be the chemical signatures of life, the physical structures that might be evidence of life, and the physiological activity that would be indicative of life. And these are the things you might measure if you wanted to understand that. The structure and the composition of the organic molecules that you might find in the surface and subsurface, any biominerals, any cell-like structures, and any isotopic indication that there might be metabolites there. The next sub-objective, the nature and duration of habitability, has this set of investigations: the availability of liquid water. Can we constrain the energy sources versus depth that life might be exploiting to survive? What is the environment so that we can understand the stability of the organic bonds that comprise that life? What is the availability and abundance of bioessential elements? And then what's the overall geological context of this place that we think we might be seeing life or evidence of past life? And I guess you guys can read through these as well as I can. There's all these different measurements that you might take: the electrochemical state of the regolith at the surface and below the surface, the availability of light, the redox potential, the temperature, the pH, the water activity that could be trying to destroy or maintain life, the availability that you might look for with a mass spectrometer of these very crucial elements. And then to understand the geologic context, you would probably be doing imaging, mineralogy, maybe even radar and E&M mapping to understand habitability. The preservation potential of biosignatures boils down to these investigations. Can you preserve organic compounds with depth? Can you preserve the physical structures that would be indicative of life with depth? Can you preserve the metabolic structures that would also be indicative of life? And these are the things you might do to try to understand that. So the second part of the life goal looked at the abiotic organic chemical evolution that you would find at Mars. And that breaks down in terms of sub-objectives to constraining the atmospheric inventories of carbon and other biologically important elements, and then constraining also the processes that organic molecules could have formed and evolved over Martian history. So looking back at this first one, the inventories of carbon, that breaks down into these investigations. What organics are on the surface or subsurface, and how do they change with exposure time? what are the atmospheric reservoirs of carbon and how do they change over time? And what is the abiotic cycling of bioessential elements? And then the last one actually is what's the bulk carbon in the crust and mantle from the Martian meteorites? And the life goal group said that they wanted to look at this question, the carbon in the crust and mantle, from using Martian meteorites. So I'm not sure that that has to be that strictly constrained to just be Martian meteorites, but if we take it for its face value, then presumably we're not going to be looking at that at the surface. We're using Martian meteorites to be a representative of the broad spectrum of the surface of Mars. But that may not, maybe that'll change in a future version of this document, so keep that in mind. These are the different measurements that you might do to address these other aspects of this sub-objective. Looking at the organics, looking at the isotopes, doing some form of geochronology at the surface, looking at methane isotopes to understand the atmospheric carbon. Are there organic aerosols at Mars? We don't know. Understanding the bioessential elements would be looking at nitrogen and sulfur species as key indicators of those, and understanding their presence and their form in the surface and subsurface, and looking at the isotopes to understand the processes that put them there. The second objective or sub-objective of this part of the life goal was looking at how the organic molecules changed over time, or may have changed over time. And so the investigations to address that would be, what are the atmospheric processes that change or create organics? And there you might look at the spectrum of light in the atmosphere, the radiation that's impinging on Mars. What would ionizing radiation do to organics at Mars as a function of depth? And again, you might want to measure the radiation at Mars as a function of depth. And you could also look at geochronology here to understand exposure ages. What catalysis would be happening to organic evolution in the mineral state? So then you'd probably want to be doing mineralogy and geochemistry of presumably depth samples, core samples that have been obtained at depth for different habitability as you get away from the surface. And then finally, people would want to look at the hydrothermal and serpentinization changes of organics at Mars. So presumably you'd be looking at assemblages of minerals to understand that, I think this is called diagenesis. See, I'm not a geologist. And looking at the organic abundances that you might find there. Okay, so turning over to the climate question. The first one, as I said, is actually looking at the current climate. The first objective is looking at the current climate of Mars, and that breaks down into these 4 sub-objectives. First, looking at the dynamics of the lower atmosphere, and then looking at the processes that volatiles and dust exchange between the surface and the atmosphere, then looking at the chemistry of the atmosphere and the surface, and then finally looking at the processes that are happening in the upper atmosphere. Now, these last 2, the chemistry of the atmosphere and the surface and the upper atmosphere, are mostly done from orbit, so I'm not going to talk too much about those. But the first 2 have some significant amount of work that can only be done from the surface. In particular, the first one, the current thermal structure and dynamics of the atmosphere, you can't really access the lowest scale height very well from orbit. And that's about 2/3 the mass of the atmosphere. So a lot of this really needs to be done from the surface. We've done a bunch of meteorology at the surface, but still our models are not particularly high fidelity. And I think that's because we haven't been making the right measurements. And so there's a set of measurements that I think that would improve our ability to constrain models and therefore better understand the dynamics that are happening at the surface of Mars. And among those, I would argue measuring the turbulent fluxes, that is the exchange of heat, momentum, and constituents between the surface and atmosphere, is a key one. Understanding the radiative forcing that is getting through the atmosphere and heating and controlling the energy balance at the surface would be another key one. And then just recognizing that Mars is a diverse planet. And so you need to have networks to understand how the atmospheric dynamics changes from one place to the next, both on small scales and large scales around the planet. At the same time, you want to look at water, CO2, and dust fluxes and how they move around the atmosphere. That one's mostly done from orbit, but there can be some contributions from the surface. Volatile exchange between the surface and the atmosphere. The first investigation is looking at dust and volatile fluxes. And again, you come back to these turbulent fluxes that I mentioned above, because you can look at how turbulence in the boundary layer moves dust and carbon dioxide and methane, for example, away from the surface of water. And then specifically looking at dust lifting process, because dust is such an important climatic driver for Mars. And we don't really fully understand yet how dust gets off of the surface. So understanding that better is something that we need to do in situ at Mars. How does dust and volatile fluxes impact the reservoirs? You might look at this, by trying to understand the processes that are happening at the poles at Mars, and understanding the surface atmosphere exchange. I'm going to skip over these because, like I said, they're mostly from orbit, and I think I'm probably not going to have time to finish this talk the way I had hoped. Let's see, moving a little more quickly. Ancient Mars. What was the climate record in the past? Yeah, let's see. Oh, in the polar regions. Sorry, I was getting a little bit confused here. What's the climate record in the polar regions? What's the climate record in the mid-latitudes? And how has the mass of the atmosphere changed dramatically in the past? The polar layers, we separate it out this way because you might use different techniques at the different places. Turning to the polar layers, polar layer terrains, the polar region, where I think probably some of the most interesting future science that's going to happen at Mars is ripe to occur. How do we don't even really understand exactly how the polar layers were formed. And so this is a high priority investigation. The only way really to do that is to sit there at the surface of the polar layers and live through an annual cycle and watch what's happening in the deposition and erosion and all the different controlling factors that are happening there. We'd also like to understand the 3D properties of these polar layer deposits. And the way you might do that is traversing across them or coring down through them and looking at the composition, the gases, the dust, the isotopes that you find in those ice cores, just like we do on Earth, and looking at the climate record that sits in that. And at the same time, you also need to do some absolute age dating of those polar layer deposits. So presumably you would want to be doing coring and stratigraphy and looking at isotopes for geochronology of that. In the mid-latitude, we also, again, want to understand the distribution, the composition, the structure of the ices and volatiles that are there. Much of this can be done from orbit, but I think you also probably need to do ground truth sampling and coring in the mid-latitudes to really fully understand this. So that's something that's in our purview here. And what are the ages of those volatile reservoirs? Again, you're almost certainly going to have to do core sampling and isotope geochronology to understand that. And then how did the mass of the atmosphere and the composition of the atmosphere change dramatically over long time scales? Well, that breaks down into a couple of investigations. When and how were the CO2 deposits at the South Pole formed? I'm not exactly sure how you're going to go about that. Some of that Pierre Buehler has addressed already a little bit, but there might also be some in situ questions that might be done. Maybe we need to core into that, or maybe it could be done through E&M sounding. I'm not exactly sure. And what you can use these polar layer deposits to understand the trapped gas composition, to look at the ancient history of the atmospheric composition. So this might be a prime candidate for ice cores. Okay, so let's see. The ancient climate processes, yeah, I need to go quicker through this, but how did the chemical composition change in the ancient past? Again, we would look at trapped gases not only in the ice cores, but also in rocks. And we might also look at how the gas sources changed over time due to volcanism, alteration, and bolides. And you might do that through geologic investigations, looking at, for example, serpentinization, and also understanding the meteor fluxes. So you might be doing some seismology at the surface to understand that, which InSight is working on, but more can be done. And then I guess there's the geologic record where you look at the ancient water cycle, presumably at maybe hydrothermal systems, You would almost certainly need to have some sort of rover there with geomorphology, aqueous mineralogy, and isotope dating, I assume, to really understand what the water cycle might have been in the ancient record at Mars. There's also a desire to understand the ancient climate via modeling, and presumably this is something that you could do at home on your computer with your GCM, but in reality you can't, because our GCMs, like I said earlier, are not all that well validated. So we need better atmospheric observations to be able to allow our GCMs to extrapolate back into the past. Okay, let me try to move on if my computer will. I jumped a slide. Okay, turning to goal 3, the geology one, and this is kind of the big one. We want to understand the geologic record, and that can be broken down into these 4 big sub-objectives. Identify and characterize the past and present water and other volatile reservoirs, document the geologic record preserved in the sediments, and constrain the magnitude, nature, timing, and origin of the transitions that obviously happened on Mars. And then finally understand the nature and timing of the construction and modification of the crust. If we just look at this first one, the past and present water and other volatile reservoirs, you can break that down into the following investigations: the modern extent of water and hydrous minerals, location, timing, and extents of the ancient water reservoirs, the structure and age of the polar layer deposits and how those link to climate, ice, both water and CO2 distribution and how those varied over time. And as before, this one I think mostly is done from orbit, so I won't go into that one more. And then finally, the role of volatiles in modern surface processes, thinking like the spider structures and the polar layer deposits, and maybe recurring slope lineae, that sort of thing. What would you do to address those different investigations? Here's a broad list of the different investigations, and this is a pretty broad set of things that we're used to seeing on today's rovers, with the addition of the capability of looking as a function of depth. So depth sampling, and this is something that would be new as well, surface atmosphere exchange. We're starting to do a little bit of E&M sounding, I guess, with RIMFAX, but it could be done in different manners as well. We do address this kind of thing now, morphology, mineralogy. I don't know that we're really doing this though, isotopes yet. Some of this may need samples. So that's another thing you've got to do from the surface. I've highlighted those a few times through this talk, but I'm not going to say a whole lot more about sampling. Presumably you need to traverse across different regions at Mars and look at the different ice, gas, sediment properties, and also sound the subsurface and the polar layer deposits to understand what is there. And then this question of the role of volatiles in modern surface processes, presumably you address that by looking for geomorphic change both from orbit and probably in situ, and at the same time doing environmental monitoring. And that would be at carefully chosen sites where we know that there's activity going on. The next sub-objective, looking at the geologic record preserved in the sediments, breaks down to these investigations, looking at the hydrologic cycles in the sedimentary and geomorphic record. And again, you'd be doing kind of basic geology to understand that, and maybe geochronology from isotopes. Looking at the diagenesis that happened at Mars, you would look at that through microscopic relationships among the different minerals that you found, the rock textures, the chemistries. Some of this may not be achievable in situ at Mars, and so we may need to do samples again on that. What would be the habitability and biosignature preservation? Again, this is something that was talked about in the life goal, but again, you do these same kind of things with the addition of organics here. If we want to understand the presence and source and fluxes of all these different aeolian sediments that we find on Mars, presumably we would need to do that by sitting in situ and looking for frequent change detection to understand exactly what's going on to drive aeolian sediments in Mars. And then, as I said before in the climate one, dust is a very important thing at Mars, driving the climate, and we don't really fully understand the mechanisms of that lifting. So I think I'm just about done, unfortunately, with time. So I'm going to have to move a little quicker here. Yeah, so this one's really huge. There's two other sub-objectives here that break down into all these different investigations. I think I probably should just skip through them quickly, but the observations that occur, that need to occur would be not only imaging from orbit, but in situ, and basically give me a little permission to just break this down as geology at the selected sites where some of these things are interesting. We need to look at paleoclimatic indicators and presumably high precision isotopes to analyze the history of these tracer elements through the Mars system. And then looking at the nature and timing of the construction of the crust. There's a whole set of things relating to age dating, petrogenesis, understanding modern surface processes, impacts on the crust, volcanic processes, how did the igneous rocks get there over time, and can we make a whole picture of how Mars evolved, given all these different observations that we do at specific localizations. We need to address all those questions, we would need to do age dating, we may need to do sampling, we'd have to look at geomorphic change, environmental monitoring, we would have to look at seismicity to understand the cratering rate, we'd have to look at the composition or morphology of volcanic outcrops, we would need to do geochemistry and mineralogy and isotope investigations as well. Let me jump forward. I'm not going to be able to do justice to this. I'm moving way too slow. I apologize to you all. The other questions then are the structure and dynamics of the interior. That one we would do via mineralogy at selected sites and seismic investigations. I think InSight has shown us that we probably need not only one lander, but a network to do a good job at seismology. Understanding the interior, again, needs more seismology, so a network, precision tracking like InSight's doing, but more of it, and a better heat flux probe that actually works this time. There's a question of the magnetic field, and to do that, you'd probably do that some from orbit, but there's a length scale that you can't cover from orbit and may not be coverable from rovers either. And so looking at the magnetometry from drones possibly, or balloons might be of interest. And then understanding the geochronology to put a timeline on that magnetic field would also be valuable. I'm going to jump past the Phobos stuff on the geology and just jump to some of the human exploration stuff. I think I'm actually kind of out of time, so maybe I should just leave it there. I would argue that this human exploration goal is probably most likely to change in the near term because of technology that would deliver us to the surface of Mars. And I think maybe leaving this one unexplored in my talk may be okay, because we're going to talk more about this in the rest of the short course. So sorry for my timing being really poor, but thanks for your attention. That's all I've got to share.
Great, thank you so much, Don. Definitely a lot of really good information. And just as a reminder to everyone, your slides will be posted so everyone can read through those goals in detail at their leisure. We'll have time for one quick question that came in through the chat from Larry Matthews, wondering about these goals and the relationship to the Mars 2020 mission and upcoming Mars sample return, and whether or not that has been factored into these, and if some of them might be retired through the measurements we can make through those missions.
So I think the goals committee in writing the document did understand that Mars 2020 had not yet been launched when we finished this, but we were pretty sure it was going to be launched. So we did understand that it was out there, but there was a risk that it isn't going to land successfully. So we left most of the things that Mars 2020 was hoping to cover as outstanding goals. And so, yeah, some of those things we should cross off, or at least lower in priority, because I don't know that it's fair to say that Mars 2020 is going to answer these questions, but it's going to contribute to these questions. And similarly, sample return, I highlighted a bunch of places where samples are important and addressing these questions, and we're on our way to starting to obtain and hopefully return these samples, but that's not done. I think it's appropriate for it to sit in the document as outstanding goals that we're hoping to do. Even more relevant, I think, to your question, there are places in the document where we refer to InSight, for example, and we still leave those as questions that are to be addressed. As we were writing it, Insight was taking observations and addressing some of these questions, but it clearly hasn't written the final chapter on those. So I think you probably, if you look carefully, you'll notice that some of those questions may have been lowered in priority a little bit, the ones that were relevant to Insight, but they're still there because there's still a lot that we should learn along those lines. Similarly, Maven is relatively recent with its returns. And that did result in some of the upper atmosphere stuff dropping quite a bit further in priority. But it's still there because there are still good questions to ask along those lines. Yeah, there's a lot in this talk, and I probably should have edited a little bit more. But I think the takeaway from this is go read the MEPAD Goals document. There's a lot in there. If you want to understand what our community has identified as important questions, it's going to take you quite a few hours to read through the document, but it's there. It's really well sorted out. So it's good stuff there.
Wonderful. Yes. Thank you so much. And yes, a big task to summarize that in just 20 minutes.
My apologies for falling a little bit short.
No, it's great. I think another takeaway from that as well was the number of measurements that, in order to address these science questions, require us to be at the surface at various locations and potentially elevations or depths. And so, thinking through that, I think helps motivate the goal to get more missions to the surface